Hello everyone, I'm Sandeep from UCLA, and in this work I'll discuss our experience in enabling hyperparameter tuning of machine learning classifiers in production at ARM. This is a joint work with Mohit Agarwal from ARM Research, Swapnil Sen Saha from UCLA, and my advisor, Professor Manish Srivastava. If we look at the production ML pipelines, these pipelines are complex and researchers often have to answer many different questions as which classifier to select from a wide range of classifiers for a particular task, what hyperparameters we want to use for these classifiers, so say, and then now the distributed training infrastructure may be on-premise or on cloud. So we often have need a system which can schedule these training tasks arbitrarily on different infrastructures, or otherwise we end up reinventing this pipeline again and again for any application. Finally, when the training has been done, we often have to deploy these models, sometimes say resource-constrained IoT devices. And in these resource-constrained IoT devices, during training time, we have to make sure that the models or the architecture we are considering are even transferable to these settings. So that question is how to incorporate these constraints during deployment. In this talk, I'll introduce 3 case studies later. So first case study is how to enable such a pipeline using an on-premise task cluster at ARM, where our application is to do bug hunting in ARM integrated circuits. A second case study is we'll discuss an AutoML framework, which is using Kubernetes cluster on the cloud at ARM. And the third case study I'll introduce how to do modal search for very resource-constrained devices like STM microcontrollers, which only have few kilobytes of RAM and flash. And in these devices, we need to consider the deployment constraints. In this entire pipeline, hyperparameter tuning is very crucial because we just end up doing retuning and retuning due to different class of models being developed, new data being arrived, or the application has, say, different needs. Maybe the outputs are evolving over time. And classifier performance is very sensitive to the choice of hyperparameter. So this task has to be done very optimally. If we want to adopt, say, existing tools or libraries, what kind of challenges do we face? In summary, the challenges are, for example, there are complex deployments in productions. So we might use local clusters or cloud computing-based systems. There are runtime failures. So whatever library or tools we are considering, they need to handle this. For example, at ARM, we had both Dask cluster and Kubernetes cluster having different applications. Another challenge is that the complexity of the search space is very large. This is because the hyperparameter space and the classifier space nowadays may be very complex. So the algorithms or the tools which we use for this exploration need to be state of art so as to save the resources. When we try to address this using existing tools or libraries, there are many libraries which are available and are open source, like HyperOpt, MacOpt, Tuna, Spearmint. In these libraries, when we try to adopt them in our production deployments, in our collaboration with R, we found that there are many software dependencies which hinder their adoption. These dependencies, for example, are the scheduler abstractions are very much integrated into algorithms. So we kind of end up tied up with the schedulers which are available in these libraries. For example, in HyperOpt, the parallel search requires Mongo workers or Apache Spark. So these tools have to be adopted by the entire application, or otherwise now there is a higher overhead in using them. Or the parallel search in SMAC requires a shared file system, and Tuna and Spearmint require a database for workers to run. And AutoScaler, which is widely used scikit library, actually provides a wrapper around SMAC. Then there are more widely used schedulers or cluster frameworks, which also have hyperparameter tuning. However, adopting this cluster framework is very high overhead. And the reason being that, for example, when we want to adopt Ktip, which is Kubernetes based, we have to adopt Kubernetes in our application, their API servers, database, and controller processes. So if the entire application is using the underlying framework like Kubernetes, it is a fine choice because application may use all the capabilities of Kubernetes. But if it's not the case, then for just hyperparameter tuning, the entire pipeline may end up adopting one more scheduler framework. And similar is for Tune or Dask-ML, where they require Dask or array cluster underneath. In light of these existing works, in this paper, we introduced Mango. So Mango is an open source hyperparameter tuning library, which is deployed in production at ARM for 25 plus months, and it's available open source. In Mango, we took very careful consideration to have a flexible architecture, so it's not dependent on any database or scheduling framework. This is basically achieved by decoupling the scheduler and the algorithmic or optimization pipeline. In our current deployments, we have deployed it on different frameworks. Specifically, the same skeleton abstractions are working on Dask and Kubernetes cluster. And we also expose capabilities to handle failures. And in order to handle the complexity of search in Mango, we provide state-of-art optimization algorithms, which are Bayesian-based. And we also evaluate and show that they are at par or perform better than existing libraries. And we also include some recent advancements which enable an efficient search across classifiers. Finally, Mango also has a cache capability, so it can do combined algorithm selection and hyperparameter tuning. So it can even make the choice of which classifier to pick. This is a very concrete Mango example, which is actually kind of complete on its own, where we first define the parameter space, and in Mango, we allow very easy definitions using Python constructs. For example, range and lists can be used. We also support directly the scikit-learn compatibility. So all these search spaces, whichever you have in scikit-learn earlier, maybe using scikit-learn capabilities can be directly used in Mango. Also, we support all the 60 plus distributions from SciPy, such as like uniform distributions. When we have continuous variables, they can be directly used. Scheduler Mango provides integration with custom scheduler that is our main objective, but we do provide serial and parallel schedulers which are integrated. So if any researcher wants to use it on their local machines, that can be done. And for optimizer, like Mango provides min-max functions. So whatever is the goal, it directly optimizes it within the search space. This is showing Mango in action. Here we are trying to find optimal log, C, and gamma parameter for an SVM classifier. And we see that the approximation by Mango, the decision boundary and accuracy with just 50 iterations is very close to what a grid search will do with 58,000 iterations. And this is how internally it's the surrogate or a Gaussian process is approximating with iterations. Going into more details into algorithms. So internally, the optimization is done using multi-arm bandit Bayesian optimizer. The surrogate function which we use is Gaussian process, GP. And acquisition function, which is created, which decides the good regions to explore, is based on the surrogate function. Specifically, we use upper confidence bound. But when we directly adopt GP, it's challenging for classifiers because Gaussian process works very well with continuous spaces, but classifiers have categorical variables or mixed integer spaces. So in Mango, we handle these categorical variables very intelligently. We do a gradient-free optimization. So we evaluate this Gaussian process only at the correct regions. And by doing some Monte Carlo sampling-based approaches, internally the optimizer is gradient-free and also is faster than the gradient-based optimizer, such as the GPY-opt. To also do parallel search, we provide different algorithms. We provide a clustering-based implementation, which is by default, which is based on some research proposed in the literature. And we also use a penalty-based approach, which is also used by some other libraries as well. The clustering-based algorithm which we implement is allow us to parallelly explore different regions of parameter space. So it can be scheduled parallelly on a Kubernetes cluster or a Dask cluster or even in local processes. How it happens is, for example, in this golden line is the function which we want to approximate. This can be any complex decision boundary. Here, for simplicity, I'm showing 1D decision boundary. And the blue line is showing the Mango's internal surrogate, the Gaussian process. As seen, it's exact at these values where we have evaluations, these cross marks. But at other places, we are having some error. And to handle this error in other places, we do parallel explorations. And these clusters are actually the surrogate function plus acquisition function. So these are the regions which we want to explore. Internally, different parallel clusters are formed. Here we are forming 3 clusters to highlight that if you have 3 parallel resources, but depending on resources, different clusters are formed and parallel search is done. These clusters are formed in different spaces of parameters. So if the parameter space is a 50-dimensional space, a cluster will be done in that space. Next, we compare how accurate is Mango as compared to, say, other libraries. So this comparison, first we use a functional benchmark. These are 53 continuous functions which are used to compare optimizers. And these functions here, the criteria for evaluation is a multiple criteria, which is based on solution's proximity to the optimal point, like accuracy, at the same time speed, like how fast can we reach the optimal solution. And these results are based on 80 iterations and they are repeated 30 times. So we are showing here the main results. And as we see that Mango is comparable to GPY-opt in performance. GPY-opt is another Bayesian-based library, which is also using GP, but GPY-opt internally is using a gradient-based optimization, which we'll see that doesn't work very well beyond functions. In functions, it is comparable to Mango, but Mango beats MAC, Optuna, HyperOpt, or random search very easily. When we go for classifiers, here I'm showing results from 3 classes of classifiers, SVM, XGBoost, and KNN. And the data sets are the ones which are available in scikit-learn, these 3 data sets, plants, wine, and breast cancer. So in total, there are 3 classifiers and 3 data sets, 9 tuning tasks. And again, we see that now Mango beats the GPY because in these classifiers of SVM, KNN, XGBoost, the search spaces are not always continuous. Next, if we go beyond a single classifier tuning, we end up in a setting where we have to do cache or combined algorithm selection and hyperparameter tuning. So the problem now is which classifier to choose even is not known a priori. And classifier type is another hyperparameter. But we still want to find optimal regions. And our goal is, for example, to prefer better classifier early on in the search. So we end up choosing these better classifiers early on and focus more on them and try to find what are the best regions for them. We saw that if we directly use multiple GPs, like for each classifier and try to combine the results, that doesn't work. So if we try to prioritize these objectives directly based on their surrogates, it is very much dependent on the initialization. Here, there are 3 surrogates are shown for Q function, absolute function, and square function, even though Q function is the best. But we see that Q function is and there are regions where Q function is worst and even worse. So wherever we initialize initially, it really decides the surrogates, boundaries. So exploration may be biased. For example, if the surrogate boundary is badly initialized, we might end up picking regions only with absolute values. And this is where in Mango, we provide a meta-tuner algorithm. So it is kind of a tuner of classifiers, which is based on a tree-based GP. So we have multiple GPs for each surrogate, which is motivated from some of the prior research. But we also use an epsilon greedy policy for exploration, where initially we explore different classifiers, but as we explore more and more, this exploration rate is decreased. Initialization is still done with random points, but finally, based on the exploration rate, we evaluate these multiple surrogates and update them opportunistically. And we also scale these surrogates. So still the GPs are updated for each classifier independently, but the exploration is intelligently done. If we compare Mango's this meta-tuner cache algorithm with some of the libraries that support cache-based search, Optuna, HyperOpt, and SMAC supports it, and we see that our Mango-based algorithm, when compared on, say, across 5 different classifiers, neural network, KNN, XGBoost, decision tree, SVM, and across different kind of data sets, it's very competitive. So Mango is kind of almost competitive here with the Optuna, where Optuna performs best. But in another classifier task, we see that another data sets, we see that Mango is better than Optuna. So it's quite competitive into the current state of art. Now let me introduce the use case of Mango. So here on the right side, I'm showing a skeleton code to highlight that the same abstractions and architecture is used across many different applications. Here, the use case is to do design verification of ARM integrated circuits. So this is a production use case where Mango is used in production at ARM. And design verification of integrated circuit is a very compute costly task. So it's in the entire development cycle, 50% of the compute actually is taken by this task itself. So whenever we are creating new ICs, 50% of the compute goes into verifying their design is correct or not. And this was currently done with a random flow. So we randomly create different input signals, which are filtered based on domain heuristics. And then finally, the failures which are found based on these simulated signals are debugged in the architecture, and this process is done again and again. But currently, based on Mango, machine learning models are used. And these models are trained in a DAS cluster where the hyperparameter tuning is done by Mango. And this models actually decides whether to use a particular input as a simulation or not. So they rank these inputs based on their capabilities or are they novel enough to decide failures. And using Mango, it has resulted in around 45% improvement over the previous deployment in terms of compute cycles. On the right, we see that here the Mango MetaTuner capability is used, where still search space is defined and objective function is now decoupled from the algorithm. And this objective function is which is scheduled on a Dask cluster. Also, the failures are handled like a simple timeout, where if training doesn't succeed within timeout, we return the partial results, and Mango allows the partial results inclusion in its algorithms. So it can still proceed further even if the complete results or training doesn't succeed. This is another use case of Mango where it's used in an AutoML framework at ARM, where this AutoML framework is deployed on a Kubernetes cluster running on Amazon AWS. Mango's role here is to spawn these different workers which are running these training tasks. And this AutoML framework is actually used to train different models by non-ML experts. So the persons who are using this training pipeline don't have to be ML experts. It's specifically designed where internally Mango does all the hyperparameter tuning automatically. And here again, the objective function is decoupled. It's the same search space has to be defined. This search space coming from the choice which for application any model is being trained for. And finally, these jobs are created. And again, we use a timeout to handle the partial completions. Here again, we show that the configuration which tuner takes from in Mango is even controllable. So you can decide number of iterations you want to do, batch size you want to use, which parallel algorithms you want to use. All those things are very easily controllable. This is the final use case which I'll discuss today, where Mango is used to train neural network models for resource-constrained IoT devices. For example, here we consider STM class microcontrollers, where the SRAM and flash are in few kilobytes. And we consider 3 classes of these hardware devices. So our goal is to find a neural network which can fit and run in real time on these devices. To enable this, again, the same Mango skeleton can be used. So there are different steps. We need to create neural network with a parameter space, whichever. This parameter space is intelligently now decided, but it doesn't have to be perfect. And based on this parameter space, Mango suggests those resources, and we kind of take care of what resources the real hardware is going to use. And now the optimization function is not only the error or the neural network training error, but how much RAM and flash is used. So based on RAM and flash usage, this optimization is now a multi-objective optimization. A scenario here which we consider is neural network trained to do odometry. So it's tracking humans using inertial sensors, and the network backbone we use is TCN, temporal convolution networks. This entire search space which we use for this case study is available officially on Mango's GitHub. This is more mathematically formalization of the objective function, where it consists of error, flash, and RAM usage. And these are lambda 1, lambda 2, lambda 3 are different weights assigned. Specifically, this error is coming from the test error of the network, but flash usage and SRAM can come from the proxy or the hardware in the loop, where we try to schedule this on the hardware and try to get the real RAM and flash. The proxy is based on some of the pure works, which are one sparse has hidden at Army Search itself, and another work at TensorFlow like Micro by Google. From these works, we get proxy or hardware in loop information, and finally, these numbers are returned to the optimizer. If we train with these settings and with Mango optimization in place, we see that for both Hopfield localization across 2 datasets, Ronin and Oxoid, as the hardware becomes more powerful, so it can handle bigger and bigger models, we see that more and more flash is being used and more flops are being assigned. Model size has also grown, but the RMSE error, which is shown here in red, is decreased. So as the model becomes more better with the quality of hardware, we're able to do better transfer. This is also shown for Oxoid datasets. In short, like Mango can enable this optimization along with bringing the hardware constraints. In summary, I'd like to conclude that Mango is available open source, and our goal is to learn and contribute back to the community. Mango provides state-of-art optimization capabilities, and it's continuously tested and improved using production workloads. And we are extending its optimization algorithms because we continuously work on making changes by doing better optimization algorithms. The entire code is available open source, and I would like all of you to use it in your pipelines.